Hey everyone, welcome to another session of CeerazzleDazzlePhysics. In today's session, I'm going to be talking about the internal resistance practical, guys. So put down today's title, it's going to be the internal resistance practical. The whole purpose of this practical is to be able to find the internal resistance of a power supply. So imagine we gave you a power supply and I said to you, how would you work out the internal resistance of it? We're going to give you a practical today in which you can work out the internal resistance. Right, before we get started guys, make sure you hit the like and subscribe button, obviously share my content with anyone who you might think is struggling in the subject. Alright, so hopefully we're good to go, and let's put down today's title and we can get started. So, here we are. How to find the internal resistance of a power supply. Well, we're going to have a quick recap about internal resistance. We know that in internal resistance, the voltage across the terminal, VT, will be equal to the EMF minus the current times by the internal resistance, guys. Obviously, make sure you understand this formula where it comes from first before watching this video, because we're going to now look at using apparatus to find the value of the internal resistance. So the first thing we're going to do is this. We're going to draw the power supply. So we know that the power supply obviously has the EMF, okay? And it has the internal resistance R over here, and we know that we're going to have a dashed line which is going to represent the power supply. There we go, so that's my power supply. Okay? From here guys, we're going to connect an external resistor, R. So here is my external resistor, R, capital R now. Don't get confused with small r for the little internal resistance here. And we're then going to put an ammeter in series with the power supply. Here's my ammeter, A, and we're going to finish it off by connecting it to the external resistor. Around the external resistor, guys, we're going to put a voltmeter. So here is my voltmeter around the external resistance R. Okay, right. Alright, so from here, we're going to do the following. We're going to change the value of the external resistance R. We're going to change the value of the external resistance R. Well, what's that going to do to my formula? Looking over here, what will it do? Well, if you make the external resistance in the circuit over here, if R increases, what's going to happen to the total current in the circuit? Well, if the external resistance increases in value, therefore the current in the circuit will go down. Because think about it. There's great amounts of traffic. Resistance is like traffic. So the greater amount of traffic there is, obviously the current will get lower. Think about resistance being traffic and current being the speed at which you can travel through it. So the greater the resistance is, the lower your current will be. So now look at the formula. What's going to happen to the voltage? What will happen to the voltage here? Well, we should be able to see that if the current gets lower, and the EMF is constant and the internal resistance is constant, then this whole term is getting lower. So the EMF is subtracting less and less from it because this whole term is getting lower. So therefore, the voltage across the terminal will increase over here. The voltage across the terminal will increase. I know some of you might be thinking, well, hang on a minute, where is the voltage across the terminal? Bear in mind, if I put a voltmeter around here, let's call this VT, the voltage across the terminals here will be the same as the voltage across the external resistance over here. They're both the same here. So let's call this one V capital R. So we know that VT will be equal to VR over here. Okay, so we clearly know that as you increase the resistance, the current goes down and the voltage across the terminal or the voltage recorded will go up. And what about the reverse statement then? So let's say if you were to decrease the external resistance, R over here, therefore the current in the circuit will go up. The current in the circuit goes up. And therefore, if the current in the circuit goes up, this whole term is getting larger and larger. So VT will obviously drop down because you're losing more and more. So therefore, VT is going to go down. So let's make a table then. So in the practical, guys, you're going to change the resistance. Let's have the resistance over here. We're going to have the current over here, and we're going to have the voltage. But obviously, guys, we don't actually need this voltmeter around here. We only need one because they all have the same value. So look, let's just put some fake numbers in here. So let's say the resistance goes from 1 to 3, 4, yeah, the current will go down. So to pick in fake numbers, 5, 4, 3, 2. And then the voltage goes up, so just making that number up again. So it's going to be, I don't know, 0, 1, 3, 4. I don't really mind. So those are some sample results that you can actually get here. But the general relationship remains constant. As you increase the external resistance, the current drops down and the voltmeter reading goes up. And obviously, as you decrease the external resistance, the current goes up and the voltage across the terminal goes down. Now, everyone, we're going to actually plot a graph. We're going to plot the graph of voltage against current. So we're going to put the voltage across here and the current across there. Everyone happy? Voltage and current now are going to be in this format. Right, so we know that as you increase the voltage, guys, we've got the voltage going up, the current will be dropping down. So we get this graph when you conduct the experiment. This is a straight line graph, guys. Okay, right, so you're probably thinking, well, how on earth am I going to get the internal resistance from here? Well, look, now we have a straight line graph, we can actually relate it to the equation of a straight line. And then we can use that to determine the internal resistance. So when you're doing this, first of all, the first thing you do is you identify the equation of a straight line. So we know that y will be equal to mx plus c. That's the equation of a straight line. Then the next thing is this. Your task is to, from here, relate this equation to the equation of the straight line. And it's almost there. So I'm going to just shift this around very slightly. So look, I'm going to put Vt underneath it will be equal to, and I'm going to put minus Ri plus E. This equation is exactly the same as this one, but you'll see the reason why. Because now look, we can match it up with what's changing on my graph to the equation. Because clearly you can see right now that if I was to circle different bits, so look, on the y-axis, you can see on my graph, it's V, and you look over here, it's also V. So these two match up. So if I plot on the y-axis the voltage across the terminal, and look, if I plot on the x-axis the current over here, there you go, so on the x-axis I've got the current, we can clearly see that the gradient of the line will be equal to minus R, which is the internal resistance. So if I were to drop this down over here, there, the gradient of this line will be equal to minus R over here. And that's how you do it. You plot the graph of the voltage against the current and you relate it to the equation of the straight line. You will find out that the gradient of the line is equal to the internal resistance of the supply. So by plotting this graph and working out the gradient, you have now found the internal resistance, guys. And if you really want to, you can find out the EMF. That is simply going to be the y-intercept. And look, if I was to extrapolate this line backwards, there we go, over here. There we go, where it meets. This value will be the EMF over here. And that makes sense because at this point right now, you can see that the current will be 0. And obviously the current is 0, this whole term goes to 0, the voltage will be equal to the EMF here. But the key thing is for you is to be able to relate the physics equation to the equation of the straight line here. So look, I took the physics equation, I knew it was a straight line graph, then I rejigged it a bit and I just circled the bits there to see what the gradient represented. And that's it, guys. And that's how you do it. That is the method to find out the internal resistance of a power supply via the graphical method. Okay, so once again from the top, quick recap. So you take your power supply, you attach an ammeter to it in series and an external resistance capital R. You put a voltmeter around the external resistance right now. The reason why is because you're going to measure that voltage across the external resistance, which will be equal to the voltage across the terminals due to Kirchhoff's first law. Then you're going to change the value of the external resistance, and we can just look at what's going to happen. As you increase the value of the external resistance, the current drops down, and therefore the voltage across the terminals goes up. And logically, if you decrease the external resistance, the current goes up, and the voltage across the terminal goes down. Just look at that equation. What's happening to I? bearing in mind that the EMF and the internal resistance are constant in this equation. There we go, I'll put some fake values here. We've got the external resistance R, we've got the current I, and we've got the voltage V right now. As you can see, as the current increases, the voltage is going down. We get this graph, yes, and it's going down here. The key bit is this: we've got to determine the internal resistance from this graph. All I do is write down the equation of the straight line, y is equal to mx plus c, and then I simply relate it to the physics equation here. The physics equation was at the top, Vt is E minus IR. But then obviously I'm just going to switch it around. I'm going to put the minus R and the I, and I'm going to plus the E. I know it looks a bit ugly down below. The reason why I've done this is so that I can relate the physics equation to the equation of the straight line. So as you can see, Vt, if I put that on the y-axis, and current on the x, the gradient of the line is going to be minus the internal resistance. And the y-intercept is going to be equal to the EMF of the cell. And that's it for another session of CeerazzleDazzlePhysics. Make sure you like and subscribe to keep my channel going. Make sure that you look over this and you make your own notes, because obviously I've done it. You've got to just try and decipher it yourself. Try and figure out why is it that it's going down in this case. Bear in mind, a lot of kids get confused with this and Ohm's law, because in Ohm's law, you know that V is proportional to I. It's not the same in this case because you are changing the external resistance. That's the reason why the graph goes down. And that's it for another session of CeerazzleDazzlePhysics. Make sure you like and subscribe to get my channel going, and make sure you make your own notes when tackling this topic, because it looks easy at the start and I've done it on one page, but make sure you understand what's going on for yourself. Alright, ciao ciao and goodbye.